Hello, this video is going to introduce the first part of Chapter 6 of our textbook, and basically we're going to jump in after having studied electron configuration. So let's just review that really quickly. Down here I have some sodium atom, so I want to write the shorthand electron configuration of that. So I have to get my periodic table. And what we do is we find sodium on the periodic table. We go backwards until we get to the nearest noble gas, which is just up to neon. And so we write that in brackets. Then I have to explain everything that comes after that. So from neon, we go forward now to sodium. And sodium's in the third period, and the S block, and it's the first place. So the electron configuration of sodium, the element sodium, is Ne3S1. Following a similar pattern with chlorine, we want to start at chlorine at element number 17, and we trace it all the way backward until the nearest noble gas, which is also neon. We always go backward, don't go forward in the periodic table, because that would imply that more electrons are in the core of that atom than there actually are. So we always go back to the sort of core set of electrons before it. Then we write everything that comes after that core. So 3s2, because we have to go through sodium, magnesium, and then jump over to the 3p block, and we count 1, 2, 3, 4, 5 boxes there to get to chlorine. So these are our electronic structures that we learned about doing in the last chapter. Now, to apply that concept, what we have when we write the shorthand notation is it tells us how many electrons are in the valence shell. So valence, to remind you, means outer electrons. Those are the ones that react when you combine different elements together. Okay, so chlorine has 2 valence electrons in the s orbital and 5 in the p, so that means it has a total of 7 valence electrons. Sodium, on the other hand, is just 1 valence electron. Every element in the periodic table pretty much wants to become isoelectric, which, to review, iso means the same, and electric means electrons. So it wants to have the same electrons as noble gases do. I spelled noble wrong. I wrote Nobel. Oops. There. Okay, so if the goal is to become isoelectronic with noble gases, that means you need to get 8 valence electrons. Okay. Chlorine has 7, so I have to ask myself, okay, would it be easier for chlorine to gain 1 more electron from somewhere, or would it be easier to give up 7 so that it would just be this neon core? And the answer, of course, is it's really much easier to gain 1 electron than it is to give up 7. On the other hand, looking at sodium, it only has 1 electron, so it's pretty easy to give that up, and when it does, it has the same electronic structure as neon. Okay, so in order for these two things to react together, what's going to happen is this electron on the sodium is going to go over here and fill in that empty spot on the chlorine. Okay, so in these Lewis dot structures, we're using little dots for every valence electron. When I draw chlorine, by the way, there's kind of a logic to it. So you put the symbol in the middle, and I know it's got 7 valence electrons, so I'm going to start by drawing 1 circle, and then I choose to draw a circle on each side before I pair them up. So right now we have 4, now 5, 6, 7. And as you'll discover later, the reason you do this is because it makes it really easy to tell where the missing piece is. This is an empty place. You don't have a pair of electrons there. You've only got the 1. So it gives us an indication of where the electron that chlorine wants is going to end up going. Okay, so if sodium wants to give up an electron and chlorine wants to gain one, and by doing that they become exactly like the electronic structure of neon, the noble gas, then this is actually really stable. Stable means good. Stable means it happens. Okay, and so this one electron from sodium transfers over to chlorine, and you're left with a positive charge. Why is it a positive charge? Okay, well, let's think about this. The element sodium has 11 protons, and so therefore it also has 11 electrons as the element. But I lost one of those to make Na, to make the Na ion here, so that means now I have 10 electrons. Okay, if you remember from chapter 1 or 2, we learned how to calculate the charge of a particle, and it goes like this: the number of protons minus the number of electrons gives us the total charge. So +1 means there's more protons in the ion than there are electrons, so it has a positive charge. On the other hand, the chlorine here has 17 protons, and it gained an electron, so that means now it has 18. So 17 minus 18 is -1. So we write it as a superscript after the chlorine. Okay, I'm going to clean up this slide a little bit so that we can fill in the next question. If you need to take these notes, of course, you can pause it and do so. Okay, so for the lowest structure of magnesium chloride, I need to find magnesium, and I look on my periodic table. It's element number 12. So that means it's in the second group. And I can just count the S and P blocks and get total number of valence electrons that way. So the first group, everything in the first group has just one valence electron, like sodium. And everything in the second group has two valence electrons. So I know that Mg can be drawn like this. Okay. And then I have, it says 2 chlorines. That little subscript 2 means there's 2 chlorines in the compound. Okay, so chlorine is, let's see, the symbol is Cl, so I found it. It's in group 17. It's also element number 17. And because it's in group 17, that means that there's 2 electrons in the S block, and then I count my way across the P, the 3p block, and you go 1, 2, 3, 4, 5. So there's 5 electrons in the p block. So again, we have this structure here with 7 valence electrons. So I'm going to write them one at a time per side. So there's 4, 5, 6, 7. So there's our 7. But this number 2 here, this subscript 2, has meaning. It means that I have 2 of these. So I'm going to put 2 of them. Okay, so now it's easy to see that there's a blank spot on each of these chlorine atoms. They both need 1 electron in order to be isoelectric with the noble gas. So the way to do that is to say, okay, well, if I need that to be isoelectric, it's got to gain 1 electron, so it has a full electron shell, and then it becomes like argon, actually. Like argon. Okay. So I can take an electron from here and move it over. Okay, and I can take an electron from over here and move it over. And this way, our product is going to be an Mg that has given up 2 electrons, which means it's got 2 more protons than it does electrons. And we're also going to have 2 chlorines with the same structure as this right here. I'm going to write the 2 in the front of it because that's how I can tell that it's an ion. But if I have 2 of them, I wouldn't write it as a subscript like we did right here, because that subscript means that is connected to each other, the chlorine is connected to the magnesium and that there's two of them. But actually what happens is these electrons move over completely, so they're not connected exactly. They're just sort of affiliated with each other. They hang out in the same place because Mg has a 2 plus charge and the Cl has a 1 minus charge. So pluses and negatives like to be together. Okay. So here's the logic of writing a Lewis dot structure. Okay, this is like a process. First we write the symbol. Okay, so I'm going to pick just a random element. Let's do, goodness, let us do sulfur. Okay, sulfur has the symbol S, and it's in group 16. So the fact that it's in group 16 means that there are 6 outer electrons. I could write the configuration for this to prove that to myself. So let's see, S is in the 3rd period 16th group, so I'm going to go all the way back to neon, like that, and then I go forward 3s2, I jump across to the 3p, and there are 4 boxes there, so 3p4, so 6 electrons. Okay, so I wrote the element's symbol in the center, and then I want to put the valence electrons around the S, and it says I try to keep only 2 dots per side. So there's 1, 2, 3, 4, 5, and 6 right there. Okay, so this actually provides a lot of really useful information. It tells us that there's going to be like 2 places where electrons can fit. That means that sulfur can form 2 bonds, or it could transfer 2 electrons to it. Sometimes it's going to form single bonds. So you might have a structure that looks something, it's a small space, but I'll try to fit it in here. You might have something that looks like an oxygen here. Well, actually, let's make that, let me clean this up, it's just hard to see. Hang on. So sometimes you might have a structure where this electron connects with one of the electrons in a hydrogen, and you get a bond, like that. We can draw 2 electrons as a line, or you can just show it as a dot. So the orange dot is going to represent the hydrogen's electron, and the purple dot represents the sulfur electron. So these are examples of single bonds. So that's a single bond, meaning that only 2 electrons are involved. Okay. On the other hand, let's see here, if I have that same sulfur, but instead of putting a hydrogen on it, we wanted to put, say, I don't know, maybe an oxygen. Oxygen has 6 electrons also, so it's going to be like this. 6 electrons. Now, I can see that, oh, I lost one of my purple electrons. Let me replace that. There we go. I can see that the oxygen needs to have 2 electrons because there's a space here and there's a space here. And I can see the same thing about the sulfur. So one thing I could do is if I connect these 2 to make a bond, and I connect these 2 to make a bond, now they're really stable. Truthfully, I wouldn't leave the drawing like this. I would clean it up a bit. So I'll redraw this so you can see what it would look like ideally. Let me change the color so it's easier to see. So after I've decided what kind of bond I need to have, one with 2 lines in it this time, I would redraw it and tidy it up a little bit. So this is a demonstration of what we call a double bond. Double bonds mean that there's 4 dots. Okay. A triple bond means that there would be 6 electrons, which we could show as either 3 lines or 6 dots. They mean the same thing.